Alright, let's work some problems. So, first problem I want to work is a manometer problem. Second is also a manometer problem, since we're dealing with pressure. We can come back and have a discussion about temperature later, but that's somewhat simpler to understand. Pressure is a little bit more abstract. So, what I want to start with is this manometer problem. So let's look at it. In the container B, we have a pressure in there, and in container B, up to the interface of where this black squiggly line starts, we have oil. The black section that I've colored in is mercury, all the way up to the spotted section, which I've designated as water. Now, something you'll notice is that each one of these has its own designated specific gravity. Now let's remember what specific gravity is. I'll write it here so that we can see. Specific gravity is the ratio between the density of the fluid that we're interested in to the density of water at 4 degrees Celsius, which for our class, we'll always assume it to be 1,000. So, if we multiply the specific gravity value that we're giving for any fluid by 1,000, we will get the density for that particular fluid that we're interested in. So, for example, in this case, the specific gravity for oil is 0.8. If we multiply 0.8 times 1,000, which is the specific gravity of water, we'll get a density of 800 kilograms per meter cubed. Likewise, we can get the density of mercury. Density of mercury is 13.56 times 1,000 kilograms per meter cubed. That would give 13,560 kilograms per meter cubed. And finally, the density of water has a specific gravity of 1, so 1 times 1,000 is just 1,000 kilograms per meter cubed. Alright, so now we have the densities of all these fluids, which is important in a manometer problem. So what this manometer problem is asking, we have a pressure in point B and we have a pressure at point A. We want to find the absolute pressure at point B, which is the section filled with oil, if we know that the pressure at point A is at 1 atmosphere and it's filled with water. So let's do this calculation. I'm going to show you the way that I like to approach these manometer problems. You may have a different preference of how to solve these. Likewise, you could do a search for other methods of solving this, but this is my particular favorite method. I find it the easiest to follow. So I'm going to write it out here as PA minus, or in this case, let me go ahead and select PB as the first pressure that we start with. So PB minus PA equals to minus gamma times Z1 minus Z2. Now, this relation may not mean much to you at this moment, but what we're going to do is we're going to traverse ourselves through this manometer, and depending on the point we start and the point we end, we're going to designate the sign convention for our height. So here we have gamma. So let's address this first. Gamma is the density of the fluid times gravity. we've calculated the densities for all the fluids. So if we multiply that by gravity, which is 9.81, we would get the specific weight of that fluid. For now, I'll just leave it in terms of gamma. So the first fluid, as we traverse from the left, remember we're starting at point B, or pressure B, since I wrote that first in the equation. So this would be the gamma of the oil times the change in height between where we started, which is at the center of point B, to where we end, which is going to be at the interface of the oil and the mercury. All right, so we started higher than we left, than where we ended up. So because we started higher, this value is going to be positive. So Z1, the first point we started at, is higher than the second point we're at. So it's going to be positive. And I'm going to convert this to meters. So I'm going to say it's 3/100. Okay? The next point we have begins at where we left off. So I'll say, and we're going to be traversing through the mercury. So we'll have gamma of the mercury, designated by Hg, is going to be, first let's determine if it's positive or negative. So we're starting at the interface between the oil and the mercury. We're ending at the interface between water and mercury. So we started lower than where we finished. So this value will be negative. Okay, so next thing we need to find is the magnitude of the value that we need to put in this parenthesis bracket. One thing I'd like to point out is that the pressure, remember we talked about in our lecture that as we move horizontally, so as we go from this location across here to the other side of this manometer here, the pressure is the same since we have the same fluid. And remember, for the same fluid, pressure is the same as we traverse across our system. Okay? So we're really interested only in the column height that has been above this location. And that height is only 4 centimeters. So I'm going to write 4/100. And the last fluid that we're dealing with is water. So I'm going to go ahead and write minus gamma of water, H2O. Let's determine if it's positive or negative. It is starting out at the interface between the mercury and the water. So the first point is below the second point, which is the last point, right in the middle of point A. So because it is Z1 is below Z2, we will say this is a negative 5/100. Okay. So now we can perform some of our calculations here. Let's go ahead and now substitute in numbers for our specific weight. So this is going to be negative 800 times 9.81 times 0.03. And we're going to be adding now. These two negative signs cancel. 13,560 times 9.81 times 0.04. And then we'll add also, since these negative signs cancel out, 1,000 times 9.81 times 0.05. So we can say the pressure difference, PB minus PA, and let me run these numbers through my calculator here. So we have minus 800 times 9.81 times 0.03. So this comes out for me to be 235.4 plus 13,560 times 9.81 times 0.04, 5320.9 plus 9810 times 0.05. So this is plus 490.5. So let's continue here. Let me add these numbers together. So this is plus 5320.9 minus 235.4. So the pressure difference between B and A is 55.76 pascals. Now the question though is asking, what is the pressure at point A? And we're specifically interested in the absolute pressure. So remember, absolute is in reference to a completely zero pressure or a vacuum. So what is it going to be in absolute values? So the absolute pressure at point A is 1 atmosphere. So we can say pressure at B minus 1 atmosphere is 101,325 pascals. Remember, we have to be homogeneous when we talk about units. Equals 5576 pascals. So pressure at B is going to be approximately 106.9 kilopascals. So that's our first manometer problem. I would like to do one more as an example here. So let's go ahead and look at another case where we have more of an open system here. So here we have flow. So here these arrows, this arrow here is showing that we have flow. Okay. And the flow is causing a pressure difference between points A and B. Now we expect pressure A to be larger than at pressure B. And what we are interested in this problem now is finding the pressure difference between points A and B. So we're just looking at a delta P. Or we can say PA minus PB. So if you look at, and what I would recommend for this problem is that you go ahead and pause it. Based on our previous example, you work out to the best of your ability this problem. Then resume it. Resume this video once you've completed it. To me, that would be the best way of learning. Give it your best shot, then see what kind of mistakes you made. Better to make the mistakes when you're on your own than when we are taking a quiz together or a test. So what we're going to do is we are going to look at the pressure difference, and we're going to use the same method that we used in the last problem. So gamma times Z1 minus Z2. All right, so delta P. So let's look at this. So we have some fluid. It looks like this is water. The specific weight is given to us for both of these fluids. So we're going to start at point A. Now from point A to point 1 that's designated in this figure, we have a height of h1. So let me go ahead and write that. So we have between point A and point 1, we have a fluid that has a specific weight, of some value. We'll call it gamma 1. And we have a height difference. Now, keep in mind, point 1, where we started, which is at point A, is lower than where we ended up, which is at the interface of our next fluid, which is some gamma 2. We don't know what it is, but you can see that fluid designated by a different striped pattern. So at point 2, it's designated on here, we have a height difference of h1. Since it's lower, we'll have it as negative h1. So our next point is, our next interface point is going to be between, we're going to start at point 2, which is the interface between gamma 1 and gamma 2, and we're going to end up at point 4 of this diagram. That height it's going to traverse is h2. So let's go ahead and write that. So we have gamma 2, and it's traversing a height that is lower, so we're starting off at a lower point. So this is going to be negative h2. Okay. The next point we have, again, is a fluid gamma 1. So I'll go ahead and write that, minus gamma 1. Now we have to decide what the sign is going to be. Now remember, the next place we start off is between the interface of our fluid, our new fluid, which is the mercury, and point B, since all the fluid is the same throughout that tube. So we start off at a location that is higher than our point 2. So inside the parentheses, we'll designate it as positive. So and that height between point 4 and point B is h1 plus h2, and that value is positive. So now that we know the conceptual idea behind this, now we can just plug in the numbers. So this becomes, with the negatives canceling out, 9,800. And I encourage you also to go ahead and write out the units for this, especially for those who are starting. To save time on these videos, I'm not going to show the units. I'm going to go through, but you can take some time, learn it now, so that in your upper division future classes, you don't have to have and struggle with knowing when the unit conversion applies or not. So H1 is 1 meter. Okay, minus gamma 2, which is given as 15,600, and this is a positive. And H2 is 0.5 meters, and this would be a negative 9,800, and H1 plus H2 would be 1.5. So let's go ahead and plug this into our calculators. So we have negative 9,800 plus 15,600 times 0.5, 7,800 minus 9,800 times 1.5. So 14,700. All right. So we would have a final value of minus 16,700 pascals. Oh, I'm sorry. I did neglect a negative sign here. Let me go ahead. This negative sign should not be here. And this value should come out to be a little bit different in this case. The reason I picked that up was because knew that pressure at the point where it's flowing should be a little bit higher than, or the pressure that's pushing it through this pipe should be higher at point A than at point B. So the pressure difference between these two is 2,900 pascals. We can use that for several things. If we put a flow obstruction here, we can use that pressure difference to calculate what the flow rate is between these 2 points. But I hope you enjoyed these 2 example problems I worked out. We'll continue to talk about thermodynamics. I expect you to know how to manipulate problems with a manometer for our quiz, for our tests, and we'll be talking more about thermodynamics here in the following lectures.